Hi there, my name is Stephen Price. I'm a PhD student studying computer science at Worcester Polytechnic Institute. Today, I will be presenting my research on data-driven optimization of wire arc DED manufacturing conditions for improved bead shape. So first, let's start off with what is wire arc DED. It's an additive manufacturing technique that uses an electric arc to deposit thin metal wires layer by layer, much like a regular 3D printer, except using metal instead of a plastic filament. Some of the benefits of this compared to traditional manufacturing include reduced material waste, lower production costs, higher energy efficiency, and rapid prototyping capabilities. So the main focus of this research is that this is a fairly new technology that has a lot of room for optimization. We use machine learning in this case, including modeling, predicting, and optimizing for processing parameters, and we focused on the shape of single layer deposits, which are referred to as beads. So some of the applications of this research: by being able to control the bead geometry, we can increase structural integrity, reduce porosity, and minimize material waste. An optimal bead is one that maximizes the width to height ratio and has no overhangs or muffin tops. And with precise control of bead shape, we can have better path planning, better layer spacing, and print optimization. So this is built on previous works which have been limited by small data sets or only analyze a single material. For example, the largest previous data set was 75 samples, and none of them have included more than a one wire and one substrate combination. However, this work, we've collected the largest bead shape data set to date with 553 samples. Additionally, this is the first multi-material data set with 5 wires and 4 substrates. Lastly, we used a design of experiment that was specifically tailored to machine learning so we can maximize the amount of information we're gaining from each sample. So looking at this, we analyzed the bead shape, mainly the width and the height, which we collected using a 3D scanner. In addition to the width and height, which are the industry standards, we also evaluated width variance and height variance, which was expanding beyond just those two metrics, and measured the deviation from the start to the finish of the bead to measure how consistent each bead was. One of the things that we did to improve performance was by doing feature engineering, in which we'd replace single categorical variables, such as a substrate name, with multiple continuous variables, considering the chemical properties present of each of the elements in each of these materials. As a result of this, we were able to increase performance by giving more information to the model and improve generalizability by enabling the model to predict on materials that it hasn't seen before. So many consider neural networks to be one of the highest performing models, and in many cases this is true. However, in interdisciplinary research, especially when data sets are small, this is not always the case. As a result of this, we evaluated many different models, including linear, nonlinear, ensemble models, in addition to a neural network. We found that a polynomial regression model, which was a nonlinear model, would perform the best for width and height, scoring an R-squared of 0.97 and 0.99 respectively. For width variance and height variance, we found that a ensemble model, specifically random forest, performed the best, with R-squareds of 0.86 and 0.66 respectively. We found that the width and height were more predictable and more consistent, which is where those higher R-squared values came in, and where a simpler model was capable of predicting these things. So in addition to being able to model this, we're seeking to actually optimize the manufacturing process. Using these models, we can evaluate every combination of parameters, even those that weren't collected, to identify their width to height ratios that we would expect them to make. And as a result of this, we can then identify the globally optimal conditions instead of just the local optimal ones based on the ones that were collected. So to summarize this research, the collected data and preliminary analysis has already been published, and the feature engineering and model performance results are currently under peer review for publication. Some of the noteworthy accomplishments include: we've collected the largest data set to date, we have collected the first multi-material data set, we've trained the highest performing models for width and height, we've trained the first models capable of predicting on multiple materials, and we've introduced novel metrics for improved optimization, including width variance and height variance.